Welcome back to Advent of Code 2021. Day 20. So last time had a bit of a rough time with problem 19. It didn't end up being that difficult. I did we don't need to talk about problem 19. There's a whole video of it, 6 hours long. You can go watch that. I wouldn't recommend it. Let's go on to 20 then. Day 20, trench map. With the scanners fully deployed, you turn their attention to mapping the floor of the ocean trench. When you get back the image from the scanners, it seems to just be random noise. Perhaps you can combine an image enhancement algorithm and the input to clean it up a little. For example, so the first section is the image enhancement algorithm. So the first is just one line, and that's the algorithm. The second is a grid. Okay. The image enhancement algorithm describes how to enhance an image by simultaneously converting all pixels in the input image into an output image. Okay. Each pixel of the output image is determined by looking at the 3x3 square of pixels centered on the corresponding input image pixel. So to determine the value of the pixel at 510 in the output image, 9 pixels from the input image need to be considered. 49, 410, 511. Input image. But the input image isn't nearly that big. Why are they using that example? Alright, well anyway, these 9 input pixels are combined. Okay, so if we want to find like this pixel in the output, we take these 9 convert them into a single binary number, and then use that as an index into this string. So it's basically kind of like a encryption. Determine the output pixel that corresponds to the very middle pixel of the input image. The 9 pixels... Okay. Alright, this is the example. Okay, so yeah. Fine. Starting from top left and reading across each row, these pixels are... Yeah, okay. By turning dark pixels into dot and light pixels into 1. Okay, so dot is 0, hash is 1. You get a binary string. That gives us a decimal index. And then you find the character, and that becomes a hash. Okay, fine. Easy enough. We can do that to get the image. So the output image will be the same. Dimensions. So if we're on the sides, I guess you just take the ones around it. Okay. This process can be then repeated to calculate every pixel of the output image. Through advances in imaging technology, the images being operated on here are infinite in size. Every pixel of the infinite output image needs to be calculated exactly based on the relevant pixels of the input image. Oh, I see. This will be interesting. Okay. So so if you've got out in the infinite space, if you've got dot 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 dot, that would be zeros. So the decimal will be 0 index, and so you take the first character, which is dot. One would hope that... Oh crap, it's hash. That makes things more complicated. So that makes our problem much worse because... So there's dots out to infinity. But if you take 9 dots... you get... a hash as your first character. They all become hashes. And then what? If you've got all hashes, then it'll be 1 1 1 1 1 1 1 1 1, which should be the last character, which will be a dot. Okay. So the infinite space alternates between dots and hashes. So after each step, they all become... Okay. That's interesting. Alright, I have an idea for how to do this. So this is way more complex than the input, the test case they've given us here. How many pixels are lit in the resulting image? Oh, we only do it twice. So it'll be dots, then after once it'll be hashes, and then one more it'll be dots again. Good, because otherwise the answer to this question will be infinite. Alright. Okay. So, how are we gonna do this? Alright. Let's just fetch the inputs. I'll write it like general form because I reckon part 2 is going to ask us to do it like a whole bunch of times, so... Alright. So... the first line is the algorithm, so it's going to be the algorithm equals f.readLine dot strip. So that's a string. Then we just read an empty line. Then make a grid. Now, I reckon we don't actually want to store it as a grid. I reckon we want to store it as a hash map, which records all the positions of the hashes. Because then we don't have to... because the grid will keep... in theory, the grid will keep expanding out into space, and everything outside of the grid will be either all hashes or all dots. So... so let's... what are these? These are lights? Pixels. Alright, we'll just say light pixels equals set. So basically storing a set of all the light pixels, ignoring the infinite ones. And then we go for line in lines for in range length strip for I. Hello, DJ. It doesn't matter what coordinate system we use here. We could use y extending downwards or just use Cartesian coordinates. Alright, we'll use y extending downwards, so we'll say Can we do this? Suppose we can. If line J is a hash, then light pixels dot add ij. See if that works. Yeah, okay. And the top left 0, 0 is a light pixel, so we should have 0, 0 in there. Which is... yeah. In an arbitrary order. What is this order? Like, you would think it would be... I thought it defaults to just putting them in order, the order that you inserted them in Python dictionaries. It didn't used to, but then they changed it so that it did, but I don't think... maybe it doesn't, I don't know. Alright, so... fine. So that's a list of the light pixels. Now, we need a marker for the infinite space, so we say infinite space equals dot. So the idea is, this says, so everything outside this, let's say we have a bounding box around this, everything outside the box is a dot. I mean, at this point the characters don't matter, so we don't need... we can just say infinite space is 0. We'll just talk about zeros and ones. So lights are ones. Everything else is 0. So let's say we have a define get pixel for a given ij. I need to take a second to think about this. Do we actually want to store the zeros as well? Because... yeah, we do. We actually want to store both the ones and the zeros. Because if we just happen to have dots all around the edges, but outside the box it's all hashes, then we actually need to know where those dots are. We can't just assume yeah. We need to, and anyway, it's basically efficient because there's almost as many hashes as there are dots. So we can say, instead of, let's call this lights and darks. Okay, so we're storing a set of lights and a set of darks. Okay. And a marker for everything outside. And then what we need is a bounding box. So basically a box. Hello, Amaro. Did I finish 19? Yes. It took like 6 hours total of accumulated time. I got there in the end. A lot of the time I was just hung up on basic linear algebra methods in NumPy and SciPy. I always get confused with those because they don't match. Some of the functions used don't match how you would do it in mathematics, or at least how you would write it in like standard expressions. So I was getting confused. Even stuff like how to add vectors together, how to add matrices together, or how to multiply them. But yeah, I got there in the end. It wasn't technically difficult. And I'm pretty sure I got the right answer the first time I ran it. It was just a bit of a slog. And part 2, oh yeah, my program was really inefficient, so it took like 10 minutes just to run it, and I figured out how to make it more efficient, but I couldn't be bothered. And then part 2 was super easy, but I just had to run the program again, so then it was another 10 minutes waiting for it to run. Guessing this one is easier. It does look easier. It's it's another game of life type problem where the state of one of these depends on the neighbors, and it becomes a 1 or a 0 dependent on that. So got a hash set of all the hashes, a hash set of all the dots. $18 minutes for part 2 was the gold, compared to over an hour for 19. As in, what, it took people 18 more minutes to solve part 2? It should be practically seconds if they had solved part 1, like, using an efficient method. Oh, okay, 20, yeah, okay. Okay, so now that we know, okay, so we know where the hashes are, we know where the dots are, and then everything outside this box is assumed to be zeros, dots. We'll call them zeros and ones from now on, because we're converting them to those. And then what? So we have we need a bounding box. We need to say I. So we have a bounding box. We have the coordinates of the highest point and the lowest point, and the columns as well. So we know exactly the full box, and everything outside that box is dots. So this method here says if you give me an I and a j, and it will return what, whether it's a 0 or 1. So basically, if I, j in lights, I mean, maybe this would have made... Okay, why did I separate these into sets? We could just make it one hash. At this point, we could just switch to one dictionary. We could say, pixels, that, and then just say pixels ij equals that. So now we just say if ij in pixels, we return pixels ij, else we return infinite space. This is just what everything outside this box is, which is going to be 0 for now. So that tells us what a given pixel is. Now we need a method of flipping the lights. So define they call it enhancement. All right, enhancement. So we're probably going to be modifying these variables. Because they'll get bigger. So first of all, okay. I_min is gonna decrease by 1. Like, the box just gets bigger by 1 space in all directions. I_max plus equal 1. J_min minus equal 1. J_max plus equal 1. Alright. And then for I in range, I_min up to and including I_max, for J in range, J_min up to and including J_max. So we are looking at the ij pixel, and to find out what it is, we look at the 9 spaces around it. We could write a get neighbors function, but this is probably the only time we'll need it, so we'll just do it inline. Or di -1, 0, 1, or dj -1, 0, 1. Okay, so that's the right order. So we can just say, so we're building a binary string. So let's just say bin digits equals, just do that now. So we look at find the pixel. So we get pixel of I plus di j plus dj. So let's start with the top left, and then we move to the top middle, then top right, and middle left, and so on. And bin digits.append that. We just put that in there. So after this, we'll have 9 binary digits. So the binary string will be just tie them up into a string plus okay, and then so the index equals the other day, when was it? Day 18? We used some binary to decimal method which didn't even have the little 0b at the start. Like, it was just a cleaner way of converting. What did I do? It wasn't 18, 17? Oh, I don't remember now. Let me look this up again. Oh, you can just do this. I thought you had to have 0b in front of it. Did they change how this works? Interesting. Okay. So that should be the index of the algorithm. So, oh yeah, we need a new pixels, and then new pixels of ij will be that. So that will give us the new set of pixels. We know the bounding box is slightly bigger. And the last thing we need to do is say, change the infinite space. Usually that's just going to flip. Dots will become hashes, hashes will become dots. In the test example they gave, it doesn't. Dots become dots, dots become dots infinitely. So we should actually just write this in the general case. We have to say space. So if space equals 0, then the binary string will be zeros, which is first index. So then infinite space is redefined to be otherwise it's one. Okay, we'll just write it like this. Just say int of 111. That changes infinite space. That should all work, hopefully. So, to solve the problem, we just run this twice. So, after we've done that, the answer to the question, how many pixels are lit? So let's just print infinite space to make sure it's all dots, because it should be. And we want to print pixels. It's literally just going to be sum of pixels.values, because there's ones for all the okay, 5014. Too low. Okay. Okay. Weird. I kind of felt confident with this one. 1, 2, 3, 1, 2, 3, 1, 2, 3. So we go back to zeros, that's good. Let me just print all the things. -2. -2, 101, 101. That sounds correct. Wait. Yeah. Oh. the one thing we didn't do is update pixels to be new pixels. Aha. That's an important thing to do. Otherwise, pixels is not changing. So we would just... There we go. So we were returning the result for one step, and that's for 2 steps. It grows slightly each time. Alright, hopefully that's right. Correct. Part 2. You still can't quite make out the details in the image. Maybe you didn't enhance it enough. Wait, let me guess. Is this going to be a YouTube link to CSI? No. It's kernel image processing, boring. If you enhance the starting input image in the above example a total of 50 times, so you just do it 50 times. Now, I think this is an efficient method, so it should just be quick. I mean, we do rebuild the entire grid, but that's the amount of work you have to do. You literally can't skip that, can you? Unless there's some clever pattern. I don't think there would be. But this is sufficiently random looking. So... Part 1. Part 2. You can just do it another 48 times. Okay. Took a couple of seconds. In theory, this should just be right, because if it was right for that, oops, for part 1, yep, just run it 48 more times. Can't really go wrong there if you've solved part 1. Yeah. Was a nice easy problem, I think. I mean, it wouldn't... It's not that easy. I think people are gonna get... I think the biggest trap... Well, it's not a trap, you can do it this way, but I think the biggest problem people are gonna run into, and I've seen similar problems in Advent Code where people did this, where they did a fixed size grid which you keep needing to make bigger and bigger. Now you can do that, but you just have to remember that the 0 point of your grid is no longer the 0 of the original image. It's kind of like -1 and then -2, because my box is getting bigger in all dimensions. So you can have a grid which represents the bigger thing, but you just got to have an offset to keep track of where the 0 point is. And space-wise, it's the same efficiency as my hash map, so might as well just use a hash map. The advantage of a hash map is it's kind of like infinitely extendable in any direction, which is really nice. And technically, you don't even need the bounding box variable. What you do, you would just have to calculate it on the fly if you didn't store it explicitly, because you need to know the top and bottom so that everything outside is a 0 or 1. But the interesting thing about this problem is that the test example, the actual question is so much harder than the test example, because the test example, everything outside there is the dot, and everything outside there stays as a dot. But in the actual example we had, everything starts as a dot, then everything switches to a hash, then everything switches to a dot out there, which makes it more complicated, because if you're calculating the edges here, you're not using dots anymore, you're using hashes on odd numbers and dots on even numbers and so on. So it's actually Just needs some more steps. But yeah, that's usually my approach to these game of life things. Just make a hash map. It just makes it so much cleaner than trying to store things in a grid. And it's super efficient when you like for the actual game of life, like Conway's Game of Life Automata. It's not dense. Like there's only a few lit pixels and the majority are non-lit. So in that case a hash map is super efficient because you're only storing, if you only had 6 pixels, then you're only storing 6 items in your hash map. You can assume everything else is empty space. So you don't need to store a grid with 1,000 zeros in it. You just store the pixels. Alright. Move on to 21. Dirac dice. Dirac. He's the one that coined the Dirac delta function. Trying to think what else he did. Dirac theorem. Can't remember what else Dirac did. I just remember the Dirac delta function, which is a very simple function. It's like Dirac delta is 1 for x equals 0, the Dirac delta function is 1, and for x anything else, the function returns 0. Is that the Dirac delta function? I think so. It's a very simple function, but it's used a lot in calculus. Something like that, anyway. Alright, Dirac dice. There's not much to do as you slowly descend to the bottom of the ocean. The submarine computer challenges you to a nice game of Dirac dice. This game consists of a single die. Wikipedia on dice. 2 pawns. Got chess pawns. Do other games use them? Yeah, I guess other games have pawns. Wait, where was... I think any piece which is sort of looks like a man with a head is just referred to as a pawn. Clue. Right. And a game board with a circular track containing 10 spaces marked 1 through 10 clockwise. Okay. Each player's starting space is chosen randomly. That is the input. Okay. Player 1 starting on 7, player 2 starting on 1. There can't be that many inputs for this problem then. Like, everyone is gonna have this a number 1 to 10 and this a number 1 to 10. So that's 100 different possible inputs. Okay, that's still a fair few different inputs. Each player's starting space is chosen randomly. Player 1 goes first. Players take turns moving. On each player's turn, the player rolls the die 3 times and adds up the results. Then, the player moves their pawn that many times forward around the track. That is, moving clockwise in order of increasing value, wrapping back around to 1 after 10. Sure, okay. After each player moves, they increase their score by the value of the space their pawn stopped on. So if the first player starts on 7, rolls 5, with stopping space 2, and add 2 to their score. Okay. The game immediately ends as a win for any player whose score reaches at least 1,000. Simple enough. Since the first game is a practice game, the submarine opens a compartment labeled Deterministic Dice, and a 100-sided die falls out. This die always rolls 1 first, then 2, then 3, and so on up to 100, after which it starts over at 1. Play using this die. Okay. Alright, fine. Play a practice game using a deterministic 100-sided die. The moment either player wins, what do you get if you multiply the score of the losing player by the number of times the die was rolled during the game? Seems easy enough. I mean, we're capped by the score, and every turn you gain at least 1 point. So, like, this is almost 1,000 turns. I guess we'll pause the input, even though it's just that. So part 1's easy. I think part 2 is going to be something a bit harder, maybe. Like, do it 1 trillion times. Just, whatever the final number is. It could be 10. So we can't just assume it's 1 digit, we have to, oops. So let me clean up 20, so we did that, get rid of that. Okay, that's it. Okay, we can just say player 1 equals, so it'd be line dot, let's say, split, take the last token, which will be like that, and f dot read line, let's take the last token and intify it. Do that again. So that's where player 1 and player 2 are. Okay, then what? So let's just simulate this step by step. So okay, so for turn in, let's say, count 1. I think we want that, starting from 1. I mean, we could just say positions equals none, none. player 1. Okay, and then just say position player 1 is that. Position of player 2 is that. So in this case, index equals turn, oops, listen, 2 just do it like this. No. What am I doing? Yeah. We're gonna have to -1, just say +1. Okay, so on turn, on this, whatever turn it is, so turn will start from 1, in which case it'll be player 1's turn. Is that right? Yeah, player 1 goes first. Roll a undecided die. Let's just say define get die. So we can just say or so while true for I in range 1 to 101 yield I. So it's an infinite generator. Every time we call it, we will get an I value starting from 1, finishing on 100, and wrapping around. Okay. So, on player's turn, we roll the dice 3 times and add up the results. So movement equals get die plus get die plus get die. This oh wait, no, this is not how you use a generator. This is wrong. How do I do this again? Dot next. Oh, how do I do that again? Okay. It's die generator equals get die. Yeah, and then you do die gen dot next. No, it's next digen, right? Like that. Yeah. Then our new position equals, so we take, let's say, Mars index, let's say -1, so that we're in the range 0 to 9, plus movement, right? And let me make sure I'm getting this correct. So we move forward. Yeah, okay. So we add the movement. And then that whole thing needs to do modulo 10. So anything above 9 wraps around. And then finally, we add 1 to get back in the range 1 to 10. That will be where our new position is. And the score will be increased by the value we stop on. Okay. So start with 0, 0. Score. Right, and then if what's wrong with this now? Okay. If the score is now greater or equal to, was it 1,000? By the number of okay, we're gonna have to have a roll count here. That's how many times the die was rolled. So, winner equals index, I guess, and then break out of this loop. So at this point, we know who the winner is, or even the loser. Oh, well, the loser is the one minus the winner. So we want the score of the loser. So it would be score of 1 minus winner multiplied by the number of times the die was rolled, which is roll count. Okay. Okay. Correct. Oh boy, here we go. Alright. Now that you're warmed up, it's time to play the real game. A second compartment opens, this time labeled Dirac dice. Out of it falls a single 3-sided dice. single die, sided die. As you experiment with the die, you feel a little strange. An informational brochure in the compartment explains that this is a quantum die. When you roll it, the universe splits into multiple copies, one copy for each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies, one where the outcome of the roll was 1, one where it was 2, and one where it was 3. The game is played the same as before, although to prevent things from getting too far out of hand, the game now ends when either player's score reaches at least 21. Using the same starting positions as in the example above, player 1 wins in that many universes, while player 2 merely wins in that many universes. Okay. Using your given starting positions, determine every possible outcome. Find the player that wins in more universes. In how many universes does that player win? Oh god. So... we are trying to work out... essentially the probability of player 1 winning. But it's going to be... okay. The player 1 starts on this, and player 2 starts on this. We're basically trying to work out what the... essentially we're trying to work out the probability that that a player wins, and if it's player 1 that has a higher probability, how many more cases does he win than player 2? Okay. And the die can be 1, 2, or 3. In this example they gave just rolling a d3 creating billions of universes. That's basically the problem, yeah. So for the example they gave, well, they started on those positions, okay. So it is basically a probability problem, but we're looking at it as number of events. But that is the definition of probability, basically. We just turn it into a fraction. We need to compute that probability, but we want the numerator and of the fraction event, essentially. So the chance of player 1 winning is going to be the chance that gets to 21 when he gets to 21, like, they can keep playing after player 2's won, but when he gets to 21 or higher, the first time he surpasses 21, player 2's score is strictly lower than 21. So we can think of the game that way. We play until player 1 hits 21 or higher. And the moment that happens, we look at what player 2's score is. So even when player 2 is past 21, we just keep playing until they're both past 21. Well, until player 1's past 21. So that makes it easier to calculate the probability. So we play until... Okay. I'm trying to think. This is I mean, we can find... What is the minimum... What is the maximum number of universes? The die rolls, basically. Every time we roll a die, they have to move at least one space. But wait, if he's starting on 7, and he moves one space, then we get 8 points immediately. This is confusing. I think this is a essentially a recursive problem. So if we know that player 1 has X points and player 1 has Y points, from that state, we want to work out how many universes player 1 will win in, and how many universes player 2 will win in. That gives us all the information we need to calculate everything. So if we're able to make a function like that, yes, yeah. If I can do that, it's basically a one-liner, the function, because there's hard to explain because recursive functions are always hard to explain. Let me try and write something down here. Okay. I want a method. Get num universes. Given player 1 score. Oh, wait. There's a bunch of things here. We need what encompasses a state? Player 1's position. Player 1's score, player 2's position, player 2's score, and one more variable, whose turn it is. Is that everything? So Describe a state. Yeah, roll count doesn't apply. It doesn't matter here. All right. So given player 1 position, player 1 score, player 2 position, player 2 score, and turn. Turn is 0, 1. Those are 1, 2, 3, 4, 5 variables here, and we're basically trying to compute this function for all possible values of those variables. But player 1 pos could be 1 to 10. Player 1 score could be like 0 to 21, I guess. Player 2 pos 1 to 10. Player 2 score 0 to 21. Turn can be 0 or 1. So it's basically 10 times 10 times 20 times 20 times 2. And we can compute that. If we can compute this for every single possible state, then all we want for the final answer is like literally the starting values, right? It'll be let's so we've got the starting values here. So this is what we want. So player 1 pos, player 1 score is 0, player 2 starting point, so player 2 score is 0, and the turn will be, let's say, 0. That's for player 1. That's the answer to the question. Well, if we say this function actually returns 2 values, the number of universes for player 1 to win and the number of universes for player 2 to win, then that will give us the 2 values, and then we get the answer from that. That's the idea. We just have to compute this for all possible values, except we don't actually have to compute it all for possible values. We just need enough to get us to this. Okay. For example, if... Yeah, okay. Okay, that makes things clearer now. So... Hello, Cat Peasant. Alright, so the base case is when somebody's score is already greater than 21. So, if it's your turn, and your score is already greater than 21, then something's gone wrong. So we assume that doesn't happen. If it's your turn and your opponent has a score greater than 21, that means you've lost. So the number of universes in which you win is 0. The number of universes which they win is 1. So that's the base case. if it makes more sense to do the indexing that I did before. So it'd be like, so we'll give a pause vector, a score vector, so if score 1 minus turn, so if it's your turn and your opponent has 21 points, then the answer to this is 0, 1, as in you've won in 0 universes and they've won in 1. Okay. And that's the only base case. It shouldn't be possible for you to call this function and it's your turn and you have 21 points already. We're assuming that will get caught on the opponent's turn previously. So then, if we reach this far, that means we're not in a final state. So we have some positions, we have some points, and we're trying to work out what happens. So basically, there's 3 universes that get created here. 1 for the die rolling 1, 1 for the 2, 1 for the 3. So 4 die roll in. Okay, and the final result we want to return will be let's say my universes and opponent universes. And we're going to count how many universes we win, how many universes they win. So 4 die roll in 1, 2, 3. Oh wait, you roll it 3 times, don't you? So and if you roll a 1, then a 2, and that's a different universe from rolling a 2, then a 1. So we actually have to do this. We have to treat every one of these as a different universe. Yeah. But we'll do A, B, C. So there's 9. Is it 3 rolls for part 2? I think the game is defined as 3 rolls. Full stop. Yeah. The only thing that changes is what the die itself looks like. So yeah. So basically we've got 3 by 3 by 3, so that's 27 different universes. 27 splits. Well, yeah, 27 universes, and in each of those we're trying to... Well, Smab UK, New Day, yeah. I just solved 20, which was relatively easy. 21 now, which is a very interesting problem. Dirac dice. I think this should work, but... caps on the positions and the scores should be enough to keep this from blowing up. Did you finish 19? Yeah. Yeah, I did. So after that day when I was streaming it, I just kind of ran the program again and then did a quick video recording of myself typing in the answer. But yeah, it was fine. Part 2 was just run part 1 again, but use whatever information I had to calculate that final thing. Yeah, 19 was a slog, definitely. So in this case, did you want to see my solution? Oh yeah, you can paste it. I'll look at it offline because I guess it wouldn't be relevant to the current problem to look at it now. Yeah, like on stream. Alright, so you sum the dice rolls, so movement equals A plus B plus C. And then we just have to do this again. We have to say so we say but we have to say all right, DJ. See you next time. New pause equals just a copy of pause. New score equals a copy of score. And we'll say pause index turn. Yeah, okay, turn equals so you -1, you add the movement, cap it at 10, add the 1 back in. And oh, so this is new pause. And new score turn is gonna be new pause turn. So now your score gets updated. And then say let's say x, y equals, and then this is where we make the recursive call. So we get num universes, new pause, new score, and then we flip the turns. And then my winning universes will be no, it shouldn't be it shouldn't be relative. Player 1 universes, player 2 universes. So here it'll be uh Yeah. Okay. And so yeah, the base case. So if the other person has exceeded 21, then player one universes will um be one if um turn is one, and it'll be turn player two universes will be one if it was player one's turn and zero otherwise. Okay, that's how I would define it then. All right. So xy equals, we call it, make the recursive call that says player one has that many universe wins and player two has that many universe wins. So we do player one universes plus equal x, player two universes plus equal y. So basically 27 different possibilities, we add those up and then we return that pair. So that is the recursive function. The most important thing is though we need to fully cache it so that we don't repeat. And then in that case, we're capped by the number of possibilities, which would be basically, it'll be like 10 times 10 times 22 times 22 times 2. So we're looking at like 80,000 possibilities, maybe. Make sure we cache it, otherwise it'll explode. At least our code looks similar today. Cool, nice. Let's hope this works then. From func tools import cache. So then the solution, say x, y equals so no, that's wrong. We need to do positions, so it'll be player one pause, player two pause to start with. The scores will be 0, 0. The turn will be 0 for player one. Oh, damn, it needs to be hashable. Oh yeah, okay, we can do that. But that means we just need to change something up there. Okay, just do list pause list score, change those, and then tuple pause tuple score. Alternatively, we could just define it on the spot as in one step, but that's fine. All right. then if that completes, the answer will be find the player that wins in more universes, and how many universes does that player win? So it should be the max of these. Don't know if have I done this base case correctly. All right, let's just see what we get. Okay, that was quick. It looks like the right kind of size. Whew, okay. That was a nice problem. I mean, it wasn't hard to code, but it's definitely the kind of problem that could stump you at first. I mean, it stumped me at first. Even though I've seen like a million different variations of this. That's recursive problems for you. It always seems like you have to do something crazy, but then it often comes just down to some form of dynamic programming. And you don't have to explore anywhere near the full possibility of positions and scores and stuff, because you only, I mean, you already start from position like 7 and so on. So that rules out like several different starting positions, and then like it's probably not even possible for one player to be at 21 when the other player's at like 3 or something, because they're both getting points as you go along, so they can't be that far apart. When numbers are huge, we expect the worst, yeah. Whoops. Yeah, that was cool. Now, just want to work out if I have time for another problem. I don't want something that's going to take 6 hours. Let's take a peek. Well, that was 2 problems today. That's a fairly okay pace. Maybe I should just leave it. Let's have a look at the stats anyway. Yeah, 19 was a rough one. 20. Alright, so that sort of indicates actually more people got stumped on part 2. That makes sense for 21. And the remaining problems seem just okay, I guess. And then, of course, there'll be fewer stars, gold stars for the final problem, because that means you have to have solved everything before. So, alright. I guess I'll leave it for tomorrow then. Yeah, just 3 days left. Cool. Where's the private leaderboard as well? Come on, Amaro, you gotta catch up. Alright, that's it then. Thanks for watching. Tomorrow, will I do it? Yeah, I think tomorrow I'll be able to. So see you tomorrow then for day 22.